let's start. Let's start. So today we are going to talk about the last part of the signal detection, which is the consistency test. And it would not be only about consistency tests, but I think it will be good to start with it. So signal consistency. Signal consistency checks. And I squared. Okay, so imagine that this is my data. Sorry, imagine that this is my template. So I have a template, looks like that. Okay, so this is the template. Okay, and here is my data. Here's my data. And I will run this template, cross-correlate this template with the data. Up, 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 up. At some point, my template is going, now it's a real challenge. So my template is going to do this. Okay, and would say, aha, I found it. Here, gravitational wave, go, publish a paper. And my role in this job is to say, that's not a gravitational wave, okay? And if you ever seen real data of LIGO, if you had played with Jonathan's exercise, you would see that this is happening to us all the time, like once an hour, okay? With a single detector, once an hour. That was what I think 02 when the detectors were more stable than they are now. Okay. What do we do? What do we do? So people write some equation. We had a model in which d of t was t of t plus n of t. And they say, aha, you found the template with the data. So you know that somehow t of t minus t0 times some complex amplitude. Okay. And let's make the template a complex number anyway. Let's make the template complex. So you know that t of t minus t0 times a real part is allegedly the data. Okay, so you take the data and you subtract that. Okay, and you say this should be approximately n of t. And people should say, what's the problem? I should just test if what I'm seeing after subtracting the best fit template. I should see if it is noise or not. I should see if this is noise or not. Now, about 70 years ago, I think, there had been a great debate. So not only astrophysicists have great debates, there had been a great debate in the statistical community, specifically about signal consistency or goodness of fit, it was called. Okay, the two sides of the debates, you know them by name. One side was Neyman, the other side was Fisher. Okay, great debate. And let's have this great debate. Can we tell if something is noise or not? Who thinks we can tell and who thinks we cannot? Who thinks we can tell? Okay, who thinks we cannot? Okay, let's see. So I have a random function in my computer that outputs noise. You could think about this random function as if it is the signs of the noise. Okay, so is it larger than 0, smaller than 0? If it is larger, I write a 1. And if it is lower than 0, I write a 0. And I have this function in my computer. And this was its output. Okay? Is my function in my computer outputting random noise? Is it random noise? Yes or no? Come on. You know or you don't? Is it random noise? It's not random. Why are you saying it's not random noise? The probability for this string, okay? So this string, let's call it data 1. The probability of data 1 is 2 to the minus n. Your favorite random noise, its probability is also 2 to the minus n. What's the problem with it? What's the problem with it? You have an h1 in your head. What is your h1? What is your h1? You're nodding.
Just that I would expect after 3 or 4 bits, one would multiply to 1. So 10%, 1%.
Okay, so you have an h1.
Bits. After 8 bits, I say it's less than 1% likely after.
So you have an h1. You have an h1 in your head that the number of zeros and the number of ones should be roughly comparable. Okay, so if you write this h1, you make a Neyman-Pearson test. Sure, you can find that this thing is not random. Okay. Here's another one. Is that a random string of bits? Oh, your test failed. Your test failed. What's the, is it random or not random? Who thinks it's random and who thinks I just cooked it up? Okay. What?
I'm with the cooked it up side.
Okay, I cooked it up. Okay. Why do you think I cooked it up? You have another h1 in your head. What's your h1?
10 to the minus 2.
That it's periodic? No, I did not ask for the p-value. Your h1 is that it's periodic, right? So you could say, here is another way a random could fail, that somebody took a random string of bits, let's say of length 2 or 3 or 4 or whatever, and repeated it indefinitely, okay? So that's a way to generate a random. By the way, the random on your computer is periodic with a period of 2 to the 32. I didn't know that, okay. At least in C. In Python, I think the period is something like 2 to the 500 or something. Okay. So this is day 2. And there's a consensus here that I just cooked it up. Oh, here is another one. Okay. Random or not random? Random or cooked? What do you say? Random or cooked? Who says it's random? Who says it's cooked? Okay, you say it's cooked. Why is it cooked? So you're saying this string of zeros is a bit too long? Is that your theory? I think in that kind of a length of a sequence, if you randomize less than 10 times, you would get something this long. Okay. It is cooked. Okay. It's cooked. If I put a dot here, you might recognize this number. Those are the binary digits of pi. Okay. Okay. Now, this had settled the great debate. The answer is no. You cannot tell if something is noise or not without an h1. You need an h1. You need to say what is it that you are fighting against. Okay? So here, it's very clear that h0, that this thing is just random noise, is rejected. Our test, our original test, we had a template, and we were asking, we had an h1, which unfortunately now is going to change to some other h1, okay? But we had an h1 that said that this is the template, right? And we had an h0 that said that the data is random noise. Now, in the decision problem, if you had to choose only h1 or h0, the test had not failed you. It said h1 is more probable. Okay? That's what the test said. That doesn't mean H1 is true. Okay? It just means that you have rejected H0 in favor of H1. Okay? But it doesn't mean that H1 is true. Yes?
In some sense, because if that's noise, the lower one, not a signal, then your sort of H1 hypothesis isn't correctly, your null hypothesis isn't correctly stated.
So when I've stated H0, I would have said NT distributes N0.
Right, and that lower thing there just doesn't.
Yes, it doesn't fit. Okay? But you know, we have the LEGO data. And it doesn't fit my equation. Oh no. It doesn't fit my equation. Is it allowed not to fit my equation? Of course. It's an instrument. Have you ever seen an instrument that doesn't have any problems? So there's a joke in optical astronomy that a detector, like a CCD, like the one you have in your phone, a CCD detector that is uniform in properties is just dead. Okay? That's the only detector that is uniform in properties, disconnected to the electricity. Okay, so this is just going to happen with every instrument, regardless of its kind. Okay. So what do we do? What do we do? Do we drop the ball and go to the sea? What do we do? So there is an exit. Okay, and the exit is to look at it. So here is one kind of a broken H0 that you look at it and you say, now I can phrase an H1. I can phrase an H1 in which the number of zeros is not exactly like the number of ones. Okay, I can phrase it. And then I can write a test. And then see if I still have insanity. So here is something that is not my signal. Let's phrase some test. Let's say something about it. Okay, who wants to be brave and tell me, how would you say that this signal is not that gravitational wave? How would you say? You know. Anyone wants to be brave? Come on. For example, if I measure an amplitude, anybody wants? No? If I measure an amplitude from here to here, and I measure an amplitude from here to here, I'll get two different answers, right? That's a test. Will it catch all possible glitches in the world? No. But that thing will not fail us again, okay? And out of experience, I can tell you that this process is kind of exponential. You begin with glitches once an hour, okay? You write your first test, now you have a glitch once a day. You write another test, now you have a glitch once a week. You write another test maybe once in 2 weeks. You write another text. In the end, you have something that you say, okay, that's it, I'm done, no more, okay? So let's go through the process, the detailed process of writing such a test. And let's talk about the signal family that we found, we as in me and Teja, but I think also Bruce, because Bruce wrote something very similar in the past, most useful, okay? So the family of signals that, the family of these alternative hypotheses to H0 that you need to make sure that you're not in one of them before you publish a signal. Okay, so let's have the general definition of the chi-square test. And note that here we are trying to see if there is some glitch. Okay, so we don't know what is a glitch. And we are trying to, so glitch is the LIGO, whatever term to all of these things. Okay, it's a glitch, your detector. It's glitching. I don't know what it means. Okay, so before that, let's have a question, which is, again, H0 versus H1. And let's use this question in order to shape our tests, okay? So first of all, again, spherical horse in a vacuum. I have a family of numbers. And these numbers are going to be denoted rows. So row 1, row 2, row 3, row 4, okay. Okay. So this will be the row vector. Okay. And I will have two hypotheses. Hypothesis 0, row vector is equal to the 0 vector plus, and here let's not even put a covariance. It's literally normalized. Okay. That's H naught. H1 is equal to some A. So it's like a two-step process. In the first stage, you randomize an A. And in the second stage, so this is A times a randomized from the unit sphere. So the unit sphere, how would you denote the unit sphere? Sn? Sn? Sk. It's K.
They actually go up, superscript and dimension.
Like that?
Yeah.
Okay. So it's a unit vector on the sphere. Okay? Literally a unit vector on the sphere. Okay? And here it's very well defined what is uniform. Okay? It's a uniform vector on the sphere. And this A, I should just tell you that it's larger than 1 in some sense. Okay, so it's a function decreasing, increasing, whatever. It's much, much larger than 1. So the scale of that thing is like a length n. Okay, so this A is much larger than any other. Okay, so if we write a distribution for it, it's much larger. Okay, so let's have a pictorial group. So this is, for example, row 1 and row 2. Okay, and H naught, I remind you there are other dimensions, but for this picture, we will plot 2 dimensions. Okay, so we have like a Gaussian in these 2 dimensions. Okay, and H naught says that, so this is according to H naught, what's the distribution? And H1 is saying that you could practically be everywhere. So you have like a much wider, much broader thing. Okay, so who wants to suggest a test that will tell me if I'm in H naught or H1? Okay, so here I apply to your physicist intuition, and we can also prove this using Weizmann if we want.
Radius less than or greater than.
Yes, exactly. So we are going to measure the radius. So if I have a sample, this is the data. I'm going to measure the radius of the data, and I'm going to compare this to some eta. So I'm going to have a decision surface. Okay, and anything that is outside of the decision surface, I would say H1. Anything that's inside, I would say H naught. Okay, now using your knowledge from yesterday and from 2 days ago, is this test optimal? What do you think? It is optimal. It is optimal, right? Because I can write probability. So let's derive it from Weizmann. The only way to say a test is optimal is to derive it from Weizmann. Okay, so Weizmann tells me probability of row vector given H1 divided by the probability of this row vector given H naught, right? And that would be, so just out of symmetry, this is literally equal to the probability of row absolute value, okay, given H1, probability of row absolute value given H naught. And now if I plot both of these distributions, it's, first of all, it's a one-dimensional thing, so now I can really plot something. Okay, so I will have H naught doing something like that, okay? So given H naught will be like that. And H1 is going to do something like that. Okay, so if this A is very, very wide, it would even not fall it would even not fall. It would rise and just continue until it will fall over there in infinity. Okay, yes? This is rho, yes.
Isn't that say this is a function of radius in both cases, therefore?
What?
Isn't it enough just to say that these probability distributions are each a function of the radius, and therefore the optimal decision rule will just be radius equals constant?
It's true, but what's the derivation? The derivation is you would apply Neyman Pearson and you would see it's a function of the radius. Okay.
But you also require that the ratio of the variables can modify hyperdefinitely.
Yes, because you are right. So I'm going to look at this thing, okay? And I'm going to say this is larger or smaller than eta. And what Javier says is that when I choose this appropriate eta, okay, I better have the ratio, the ratio function, I better have it to be monotone so that I can just say radius larger than eta and not ratio larger than eta. This is totally correct, and this is why I did not say super explicitly why it is A, because, okay, there's a sensitivity there, but you're right. Okay, so this is the chi-squared test. It's still not a chi-squared. Now it is a chi-squared. Okay, but this is a monotone function. I'm applying a monotone function. Okay, if I apply a monotone function, what do you care? Okay, and good. So let's continue. Okay, so we know how to test if something is 0 or a bunch of numbers such that the overall amplitude is the same for all of them, but the phase is random. Okay, their position in n-dimensional space is random. Okay, so who wants to suggest a test for the signal consistency of the gravitational wave? Who wants to suggest it? Okay. Actually, let's put it here. Somebody wants to be brave? Okay, so we have the T dot D, okay? And we called it rho in the past. Now we are going to take this template and we are going to partition it either on time or in frequency such that the following happens. We are going to write T as sum over I, Ti, okay? And we are going to say the following things. And maybe this is a 1 over square root K, okay? Okay, and we are going to say the following. We are going to say Ti with the same angle brackets. So I remind you that angle brackets is sum over frequency, or maybe not sum over frequency, just Ti C minus 1 Ti, okay? So this is, I need a complex conjugate at some point. Let's put it here, why not? Okay. So this is this Ti. This is the meaning of it, and it's a complex template. Okay. So Ti is delta Tij is delta Ij. That's requirement number 1. Okay. And that's, well, those are the 2 requirements. 1 and 2. Okay. So now if I denote rho I to be the match of the data in Ti divided by the square root Ti, Okay. Those are going to be my rho I. And let's see what are their properties. Okay. So now it's going to be very confusing. H0 previously had no signal, and H1 had a signal. Now, after we have decided that H0 is dead, we have H1, and H1 is telling us that there's a clear definite template. Okay, so now there's H1 and H glitch. Okay, so let's start with H1. H1 is saying, so rho I given H1. Okay, so I'll write it in the previous language. H1 says that rho I distributes a normal variable with expected value rho divided by root n. Okay, so this rho, by the way, it was a complex number, and it has a, so this is the same complex number. Okay, and these are also complex numbers. Okay, so I should say complex normal with a distribution rho over root n as the expected value. And here I have a identity matrix. Right? Why is there an identity matrix here? It's because I've made sure that Ti.Tj is delta ij. Okay, so that thing would have been in this covariance matrix. Okay, so now this is H1. What does H glitch say? H glitch, what does it say? Rho I distributes like, I don't know. Who knows what's a glitch? I don't know what's a glitch. Okay, but I've seen one glitch. In this one glitch, what was happening? I had, so if there's a partition of this thing to several groups, okay, so some of them had different amplitudes than the other, and also the phases, who says that they are right. Okay, so we found this to be a useful test to just say that this is a complex normal, and what else did we want to say? Complex normal, and it has a bias value of rho divided by root n, just because, okay, so this bias value is actually saying the following. Maybe I should go slower. So rho I minus this thing is complex normal 0i. And we would say that rho I minus this thing is a complex normal, and I don't know, 10 times I, whatever. Okay. Now, is this hypothesis correct? This HG? Is it correct? It's not correct. There's no correct. It is useful. It is useful to say that this thing is not a gravitational wave. Okay? Now, is there hope for me to find the correct H glitch? Maybe, if I understand the physics of glitches. Okay? But for any kind of glitch from an undefined family, no. Because remember this pi glitch. If I know nothing about pi, okay, I would never guess that this string is not random. Okay? So in order to say what is not a gravitational wave, you either need the physics of the glitch or the empirical, I don't know, examination of, you know, the zebra, the elephant, the lion that come your way when you analyze these gravitational waves. Okay? Okay. Good. Now that you know everything you need to know about the chi-square test, I should say a few cautionary words and a few rules of thumb to help you design your own chi-square test if you ever need one. Okay? So first, caution. Who told you how much is K? No one. Is it good to choose a big K, small K? What do you think? Should I strive to a test that has as many Ks as possible? Javier is experienced, he says no. Bruce is experienced, he also says no. Okay, why? Bruce, why?
Because then your chi-squared statistic is not very large. You're treating with very small
Exactly.
offsets of each one. And it's
Exactly. We have a budget. Our budget is this row that we have seen in the detection of this alleged template that we have found. We have some row. This row is going to be, I don't know, 10, no more. Okay? And you care about this only when the signal is kind of faint. So 10, 8, that's your budget. Okay, now if you are taking something of length 8 and you are putting it as a vector in 64-dimensional space, you have very little budget for every dimension. Okay, and that's what Bruce said. So let's formalize this. Okay, so this thing is called the chi-square test because the probability of so what is going to be our test? We said our test is going to be sum over I, rho I squared, okay? And maybe I should say rho I minus rho average, okay, squared. So this is going to be our test. So this thing given, and here I will write H1. Now remember, H1 is the signal hypothesis. It's not the glitch hypothesis. I'm sorry, I just didn't want to kill you with flipping the meaning of H1 and H0, but I am killing myself. So sum over I, rho I minus rho hat, given H1, that distributes chi-squared, which is K minus 1 times 2 degrees of freedom, okay? Now it's easy to understand why it's K minus 1 times 2 degrees of freedom. First of all, just how many numbers it's K times 2. And you never knew rho hat to begin with, so that reduces the degrees of freedom. There's a formal way of saying this, and I will upload some part of my notes in which it will explain like this degree of freedom shenanigan. But in any case, that's a distribution, and if you really don't believe in math, you can just simulate it. Okay. So this is literally the definition, by the way, of chi-squared. So it's kind of a tautology. Okay. Okay. So this is why it's called the chi-square test, because of the distribution. It's a very bad misnomer. So we have this test, and we said, okay, so what is going to be the distribution of this HG? So this HG, we could think about the possibility that we might have had a template, okay, for a glitch. Okay, so let's call this TG. Okay. And if I dot TG with the data, okay, I will get rho G. Now, if I had a template for that guy over there, okay, and I had to make a decision, a binary decision between this glitch with this template TG and the gravitational wave with that template, how would I make this decision? Neyman Pearson. What would Neyman Pearson tell me to do? Neyman Pearson would send me to do something like that. So I would do e to the minus half d minus t g squared in, not squared, c minus 1 d minus tg. And I would divide it by e to the minus half d minus t c minus 1 d minus t, okay? And after some algebra, okay, you will get a test that looks like d c minus 1, and I will have tg minus t, okay? So this is what's going to happen, okay? And what I want to say is the following: rho g is larger than rho for the case of the glitch, okay? So this is this H glitch, okay? Now, if I have chosen the number of beans to be such that, okay, so if I have chosen my partition of the signal in time or in frequency domain such that within a cell of the partition, the template and the glitch are indistinguishable, okay? If I've shown that, and that's a big if, because who says I did, okay? If I have chosen like that, then the distribution, now, by definition, rho g and rho, it's not even a close competition, okay? Because if it's a close competition, then you can actually not know if this is a glitch or gravitational wave. How would you know? Nyman-Pearson says you can tell the difference. Who are you to tell me that it's a glitch or a gravitation? You don't know. Nyman-Pearson doesn't know. Optimality comes both ways. Okay, so by definition, rho g is much larger than rho. I wouldn't say 100 times larger, but larger substantially, okay? And the probability of this sum over I, rho I minus rho hat squared given by hg is going to be, and remember the assumptions. So k beans resolve the glitch. Okay, so that's going to be rho glitch squared. It's going to be, sorry, a non-central chi squared. Who knows what is this madness? Non-central chi squared. I think if you want to apply it in the computer, it's literally NCX or something like that. NumPy dot scipy dot stats dot NC. Anyway, non-central chi squared with a non-centrality parameter rho g squared minus rho squared. Actually, I don't think there is minus rho squared, comma, k minus 1 times 2 degrees of freedom. Okay, so those are degrees of freedom. Degrees of freedom. And this thing is non-centrality parameter. Okay, so this is what's going to happen to you. And here there's a big if that you actually resolve the glitch. Okay, but suppose you do resolve the glitch. Then let's make a plot. So we have distribution given h naught. We have distribution given h1. And it's a one-dimensional distribution. We could really make the Nyman-Pearson optimal choice. So h1 says that it looks like that. Okay, so that's a chi-square distribution. So this is this chi-squared. Okay, this is sometimes called the chi-squared. I'm sorry. Okay. Notice it's unnormalized. I don't know why people normalize chi-square distributions. So this is a chi-square distribution. P of chi squared given h naught. And now let's plot in a different color. So this is a non-centrality parameter. You will have something like, okay. So this is P of chi squared given h1. H, unfortunate. I told you I'm going to miss this. Okay, so this is h1 and this is h glitch. Okay. Okay, and there would come Teja and tell me, Barak, you better not throw the real gravitational wave. And I would say, what does that mean? I know what it means. It means that the integral from infinity until my eta, okay? Teja is a very conservative person, so we would want the integral from eta to infinity of P of chi squared given h1 d chi squared, okay? We would want this to be smaller than 10 to the minus 4. 10 to the minus 4 is a number that Teja told me. Okay, so we have a test, and we know how to put a threshold. And now let's see the dynamics. What happens if I make k smaller? Okay, if I make k smaller, then I would reduce the number of degrees of freedom. If I reduce the number of degrees of freedom, the chi squared goes to the left. Okay, so this thing goes to the left and becomes narrower. Okay, and as a result, the eta is moving left. And what happens to the h1? The h1 stays in the same place and becomes narrower. So my ability to tell between the distribution is much larger. But this assumption might fail. Okay, so again, it's an art. Okay, you need to look at the glitches. You need to choose the partition such that you will resolve the glitch. Okay, and then you design a test, and then you enforce the probability to throw an actual real gravitational wave. Okay. When we did this back in the day, in that building, we found most useful the tests that have only 2 degrees of freedom. So how can this test have only 2 degrees of freedom? We've said the following. Look, here is a gravitational wave. It's chirping. So I'll shoot it back at you. If the stationary phase approximation applies, what does it matter? Right. So it only matters when the signal is extremely short, and we anyway did it in frequency domain just because it was also easier to make the different parts of the waveform orthogonal to satisfy this in frequency domain. But I mean, it is what it is. Yes, so what is a gravitational wave? A gravitational wave is something that has some amplitude as a function of frequency. That amplitude can actually, so it's barely measurable anyway. So you have something in the bucket, right? And you have an amplitude that is going to do something like that, okay? So this is, I don't know, orbital hand gap, whatever. Hand gap. And this is some cutoff frequency. So what I'm trying to say is that the amplitude, so this is A of f, and this is frequency, okay? So what I'm trying to say is that this is frequency, okay? What I'm trying to say is that this A of F is actually not the informative part about is it a gravitational wave or not. Glitches will do it as well, okay? So this A of F is actually very similar to 1 over F. And you know what also has a spectrum of 1 over F? Like if you have a delta function jump in the sound, okay? It has a 1 over F spectrum, fact of life. Okay, so this A of F is actually not going to help you so much. But the thing that will is the phase evolution. So a gravitational wave chirps. This chirp. Did I do it correctly? No. There's absolutely no chance, even if I try 100 times, that I will manage to chirp correctly a gravitational wave. Because that phase is detailed. It is very detailed. I can try morning and evening and would never be able to chirp the gravitational wave correctly. Okay? So what does it mean? It means that I need to check the phase. So I have these row i's, and what me and Teja found is that if I take the phase from this part, and I take the phase from that part, okay, that's a test. I'm comparing two complex numbers that I know should have the same amplitude and the same phase, and I'm just checking, are they matching? So I'll just, so the way this test looks is that you are looking at some row. So let's define some, I don't know, row left, which is the sum over I equal I smaller than I left, okay, of row I. And I can define a row right, which is the sum from I right, I larger than I right, okay? And I will normalize them. This is divided by, not square root, by IL. And this is divided by, I don't know, K minus IR. Okay, so those are two numbers. They better be the same. And I will just look at row L minus row R, absolute value squared. And H naught says it's exactly at 0. Okay, so this is chi left right. I don't know how to call it. Okay, so this chi left right is a complex number. H naught says it is here and gives me some standard deviation. And H1 says, well, wherever. Okay. Okay, sorry. This is H1. At some point I will figure it out. And this is H glitch. Okay. And I will just make a test, and my test is going to say, is it larger or smaller than something? And I will enforce this 10 to the minus 4. Because it has only 2 degrees of freedom, I could really detect really, really faint glitches or in agreement, okay, disagreement. Very small disagreements I can pick up, okay? And we found that a series of these tests is the most sensitive. And the general test, the tests that have 100 degrees of freedom, we found them unuseful. But you know, there's more than one way to do it. So you remember these pies. So if I had to come up to you and say, make me a test that will also reject this pi, one person would say, aha, I have a dictionary, I know what is pi. Another one would come and say, come on, you can do better. This thing, if you develop it as a continued fraction, you would see that at some point the residual is too small and you will make a test about that. Okay? It's more general. Will detect E as well. Okay. Okay. So I think we are finished with chi-square test. And let's move to the next steps on the pipeline, and let's see how much time do I have. I have 25 minutes. Good. Very good. Enough time, I think. Okay. So I remind you where we were on the pipeline. So we had a template bank. We had a set of templates T1, Tn bank. We had a set of templates. Yes. Yes.
If you have these two segments, you need to estimate the phase of each one of them and see if they are consistent. So
We are actually comparing the complex number because, you know, the amplitude can still also not agree. Okay.
but when you do that, do you need to take it to the next step of parameter estimation for each part of the signal independently, or do you use the same band that you're describing this small?
I did not understand the question. Again?
So when you split the signal to two parts and
Yes.
compare the phase at each one of them, you need to get a good estimate of phase at each part of the signal.
From the signal. Yes. So in fact, if I have a perfectly valid gravitational wave template that is just not the template that I am currently employing over the data, it might also not pass the test, which is fine. My test is asking, is this part of the data a detection of that template? And it's perfectly fine that the answer will be no if there's another template that will pick it up. So I assume that the moment of gold, the moment where it matters is when I'm considering the right template. The template from the bank that represents the actual gravitational wave that is in their data. That has to pass. All the rest, they can fail. That's their problem. Okay, but that has to pass. Okay, did I answer your question? Okay. It is also true, by the way, that even this guy is a non-central chi-squared with the mismatch. Okay, so if I have a mismatch in my template bank, let's say 5% or 3%, or whatever it is that we have chosen, that mismatch is also going to be a non-centrality parameter for that chi-squared. If you go into the code of Teja, he has two non-centrality parameters that are getting compared. Okay, it's there. Okay. This is very important, otherwise the 150914 will go to the trash because it has such a big amplitude that even the differences inside the template bank they are small, but they are big enough to make a difference, and you might actually reject it. Okay, you have to be really nitty-gritty about these things. Okay, where have we been on the search? So we had a template bank, and we ran it over a year of data. Okay, and we did it with several detectors. Okay, and we kind of stopped by saying, you just match filter. Okay, and there's two things I wanted to say. So first of all, there are glitches. Okay, glitches, monsters. Okay, so these glitches, if I now plot the rho square, the match filtering test of all these templates, I bunch them all together and ask how many times each thing happens. I have a prediction from H naught. Okay, no signal. This is my prediction. And I have a measured distribution. Is that gravitational waves? Is that gravitational waves? Maybe. Depends on how good I've rejected the glitches. Okay, so I don't know. At some point, there would come a time your advisor says, that's it. We are publishing. I don't care. We have to publish. You are not writing another glitch test. Don't do it, okay? And you have to live with the fact that your prediction, your H0 prediction is wrong. Okay, so what do? LIGO thought about it ahead of time, and they have built 2 detectors. Okay, the geometric localization where it is on the sky, I think it's an excuse. The real reason is this. You have to have, so this is row Hanford, and there's another row Livingston with a similar prediction and something like that. Maybe not in the same point, by the way, maybe it continues even further. Now you know it's glitches, okay? And what do? How would you say that something is a gravitational wave? Okay, so the patent of the LIGO collaboration was to say a gravitational wave that better move at the speed of light between the 2, like, and the delay between the 2 detectors, the maximum delay is the speed of light delay between the 2 detectors. Okay, so the time it takes light to fly from Livingston to Hanford through the Earth. Okay, so that's the maximum time between them. So now if I want to say something, I would say maybe I want to use rho L squared plus rho H squared, and I want to compare it to some eta. Okay, and okay, it's not a bad strategy. If you follow Nyman-Pearson using that prediction, you would actually reach exactly this conclusion. Okay, right? Because this was a likelihood ratio, this was a log likelihood ratio, and this was a log likelihood ratio. Adding them is just like multiplying them. And multiplying probabilities means that you believe that the detectors are independent. Okay, so this is what Nyman-Pearson of H0 versus H1 will tell you to do. Okay? Exercise. It's not a hard exercise. Okay? So you do this, and then again, you make a plot, okay, of rho L squared plus rho H squared, and you have a prediction. Now the prediction is a 4 degree of freedom, so it's not a pure exponential like it was there. It's more like that. Okay. So let's plot it from the interesting point alone. Okay, so this is rho, I don't know, rho squared equals 50. Before 50, there's no point. And over there, it's already exponential, and that's the H0 prediction. And again, you measure this thing. Is that gravitational waves? Yes.
So just to understand the setup, you test each one of the detectors individually, and if both of them test the threshold, only then you apply the joint.
No, I'm just checking together if they pass the threshold. That's what Nyman-Pearson is going to tell me to do. Nyman-Pearson does not enforce a single detector. Yes. This is just the thing that is happening. I'm showing you a distribution. Okay? Good. So, is that gravitational waves? I have 2 detectors and I do this. Is that gravitational waves? No. Still not gravitational waves, because if I take something from here and I add to one of these average guys that just happened at the time of this big thing, okay, that would still reach here. Okay, just because, you know, it already had 100 from here, so maybe it gets here to 107. Still there. What will you do? What will you do? So first of all, there's a foxy thing called time slides. What is time slides? Time slides tell me, just repeat the analysis with the detector's offset. I know that the maximum time delay is like 10 milliseconds. Just repeat it with an offset of the detector. And with time slides, yes. Excellent. And with time slides, I get that distribution. Okay, so now what is gravitational waves? Is this guy gravitational waves? No. But is this guy gravitational wave? Yes. Now you know it's a gravitational wave. So you have empirically measured what are the actual properties of the background. And you have reached this blue distribution. And now your empirical distribution of what really happens when the detectors are aligned. Now you see the gravitational waves. Okay? Is that an optimal test? No. How much did we lose? How much did we lose? We should have had a detection limit. Okay, we should have had, so if these are gravitational waves, now that we know that there's a gravitational waves here, okay, we should have had a eta optimal over here. And what we had is eta practical, which was over, I should say something like that, okay? Eta practical. Okay, so what is my loss? My loss is going to be some power of eta practical, eta opt divided by eta practical, okay? So you would say, I can now look at the LIGO paper and see how much have I lost. This eta opt, you can actually compute yourself. I did it. Okay, you could actually compute how much it is. Okay, and if you look at the O1 analysis, you look at the actual detection limit versus the optimal one, you see that the difference was much more than 10%. It was, I think, more than 15%. Okay, so there is room to do it. Okay, so how can you improve? You see these guys, and you see what happens with them. How do you improve? I'll make a two-dimensional plot, and you will see it right away. I hope I didn't break anything. Okay, so this is rho h squared, and this is rho L squared. Nyman-Pearson of H naught, the test from H naught, tells me that I should have a decision boundary that is like this. So the probability distribution exponentially decays like that, like the sum of rho L squared and rho H squared. Okay? Now, if I take this 1D distribution and this 1D distribution, okay, I will get a practical distribution that looks kind of like that. Where do gravitational waves pop up? Gravitational waves pop up okay, and what corresponds to that decision boundary? This H practice. So that was the previous decision boundary. Okay. Now I ask you, why did I put this decision boundary here? I did it because I saw that graph. Okay. But now, when you look at this diagram, is that a gravitational wave? Yes. What can I do in order to save it, salvage it? What? Remove glitches is one option. It's a good option. Okay. But I told you, your advisor already told you, Ariel, you have to finish. The final report is tomorrow. You cannot remove more glitches. That's it. Okay? So what's the way? So you remember, if nothing works, what you do is change the question. Okay? So how do we ask this question the Nyman-Pearson way so that we say, aha, okay, given the thing I already have, this is the best way. I would say, okay, here is two variables. I already forgot how they were formed. This is row L and this is row H. This is their distribution. Now let's say Nyman-Pearson, how does H1 look? Nyman-Pearson, how does H0 look? Okay? This time, you will have to estimate what's the probability density of this guy, including this tail. It doesn't come from an equation in your computer anymore. It comes from the actual data of the detector. And what you will get is a decision boundary that now looks like that. That will be the new decision boundary. Okay? And in terms of equations, what does it mean? It means that you have, instead of row H squared plus row L squared, you went to some function of row H squared plus some other function G, this is GH and this is GL of row L squared. Okay? And what is this GH? Nyman-Pearson tells me to look at probability density. So this GH is equal to the log of probability of row squared H given H0 plus H glitch. Now, I don't know how to phrase H0 plus H glitch, but what I do know is how to measure it Monte Carlo, and that's over there. Okay, so I just need an estimation of what is this probability density. And then I have Nyman-Pearson is telling me there's only one thing to do, and that's this. And after changing the question, it's very clear that this is what I should do. And indeed, that salvages a lot of these gravitational waves that were lost. So previously, the optimal detectors, if you had more time and had reduced all the glitches, that's the optimal thing. Okay, so that would be this eta optimal. Okay, in the past, before we did this correction, we have lost all this area. All this area was lost. Okay, and now that we changed the question a little bit, we lost only that area. Okay, we still lost something, but much less. Okay, good. So now, in the IIS pipeline, these things were called rank functions. Rank function. Because basically, if you look at what's happening here, you're extrapolating the rank, whatever. Okay. I think PyCBC also has a similar thing, and I think also GST-LAL has a similar thing by now. In 01 and 02, I don't think they had, but now they have. Okay. So what are we left with in the last 5 minutes? So in the last 5 minutes, let's talk about the outlook of searches. And where do we go from here? And maybe in the last 1 minute, I'll try to save you from your advisor. Okay. So where do we go? I think pipelines of gravitational wave detection are already in the diminishing return point. Not because I'm too proud of myself. It's because we know where is the optimal decision boundary, and we know what we can and cannot detect. And there's already diminishing return. We know what's the we don't know how to get the gold out of the pot, but we know how much is there, and we are okay with it. I'm okay with it. And so what do we do? Do we go to the beach again? And you remember this template bank? You remember that this is, we built it only from these two waveforms, and there are some effects that are not in the bank. One effect is higher modes. So Jay from our group had tried to extend all of this to the situation where the template was from a richer family of templates. And he did it successfully. And why did we go to these higher modes? They are anyway a small perturbation to the SNR. The reason was that if you go to the very high masses, you would see that higher modes begin to be very important. And if you have some question about what is the mass cutoff of binary black holes, then higher modes is the access to this, is the key to access this phase space. Another question, people ask the question, are binary black holes coming from dynamic formation versus binary stellar evolution? And there's a clear prediction for dynamic formation. The clear prediction is that the spins should be isotopic, which means that there should be processing signals. But are we looking for processing signals? The bank is built out of no processing signals. Moreover, what is a processing signal? It's a signal that instead of being a regular in spiral does this. You remember from Patricia's talk? I am actually testing that this is not happening in my chi-square test. Oh no. You could think of processing signal as if it is a raw glitch. This effect is not so severe, but it could get severe. Okay, so we have pipelines that currently reject processing signals. Will we be able to resolve this question? I don't know. In order to do it, we have to first characterize the pipelines that we do have, which I think LIGO is doing quite well. But a better solution is to just find them all. And here the key element that is missing is this 15-dimensional integral, in which you have a score at the second stage that takes into account all the effects of higher modes and precession. And until now, I think it was unfeasible. But due to the work of these two people, Jonathan and Javier, we now have a way to compute this integral in a minute, 2 minutes, few minutes. And that means that we can pass some of the order, I don't know, 1 million candidates to Jonathan and Javier. They would compute this integral, and we'll manage to detect processing signals. And this is where we go. Where we go afterwards, I don't know, maybe more complex signals. But this is what, this I think is the forefront. And the last thing, 2 minutes. 2 minutes to save you from your advisor. There's one thing I've seen in gravitational wave field that is missing, and I should have thought, but I didn't quite understand that I should, but now I do. Is to count information. So information theory, you could take courses in information theory, and I'm gonna give you a cartoon of a cartoon of a cartoon of information theory, and just tell you that, first of all, rho squared, which sometimes is called SNR squared, that's an additive quantity. So that means if I add more and more sources of information, the optimal way to combine them will have an SNR that is the sum of the SNR squared of the individuals, okay? And also, there's a unit to this thing, okay? So after a constant, the unit is bits, okay? This constant is like 0.7, I think. Which means that if you have enough SNR squared, you can measure if a bit is up or down. And how many bits can I measure is this SNR squared. Okay, so this is the Shannon theorem of channel capacity. And what do I want to say this? Because there's a question that always comes in gravitational wave astronomy. Measure me the tidal deformability of the neutron star. And then what you should tell your advisor is, let me compute something. Tidal deformability, here is frequency, and you have this cartoon, and you have that cartoon. And tidal deformability for a reasonable equation of state makes a change that is larger than, let's say, 0.2 radians or something from here onwards, from this frequency onwards. And you should take the signal that your advisor tells you to measure the tidal deformability and take this frequency to infinity and ask, what is the integral of A of f squared divided by Sn of f from this f tidal deformability minimum, I don't know what to call it, to infinity? If that number is smaller than 1, you should say no. No. Now they would tell you, nah, but you have all these Fisher.
Just to be
No.
clear, you need a factor of 4 in df. Yes.
Okay. Df, and you want a factor of 4. Fine, I will accept this. But that means there is, if you see this thing, there's less than 1 bit of information in the entire data set that is supposed to contain something about this phase shift. Now, he would show you the Fisher information and would tell you, but I should be able to measure it to this df. And you should say, no. You cannot measure 1 bit of information. Okay? I have been in a conference in which there was a session with 10 different people trying to measure this. Well, this integral was never mentioned. Okay? Yes?
So suppose if somebody shows me some very fantastic set of corner plots,
Yes.
how can I tell how many bits of information are there? Or better yet, how can I blur that with my eyes to say, okay, I know from SN arguments you can have more than 30 bits of information. How do you
Okay, another cartoon. Here is the following.
Please rephrase my question.
Yes. So let's make a cartoon out of this question so that it's very clear what I'm talking about. So if I have a sine omega t plus n of t, okay? And let's make this a here such that the sum over t of a of t squared is smaller than 1. Okay? Can you measure this frequency? The answer is no. If I run a corner plot that this sampler, whatever, trying to sample omega, what will I get? I'll get something, so it will get fixated in some place and you will see something like that. But if you actually did the brute force enumeration, you would see that actually there's really no information and you cannot tell where is this omega. Once this thing, instead of 1 being 5, you would be able to pick out the right omega out of 1,000,000, okay? And then suddenly your measurement will be good. Then this Fisher information will actually predict what is the error bar on this omega. But before that, it has to be detected. And this thing, SNR squared, larger than 1, for every question, deviation from GR, tidal deformability, precession. If you don't have enough SNR squared, don't even start the run of the corner plot. Return to your advisor and ask for another task. Okay? Good. Finished saving you for an advisor. I think we are done.